In the first week of chemistry, we covered quite a bit of material with a couple labs and a few discussions, and I wanted to summarize that real quick with a few notes. So, chemistry is the study of matter, and of course, matter is anything with mass and volume. Mass is a measure of the amount of substance, how much particles, if you will, or it's made out of. Volume is the amount of space that something takes up. Weight is not mass. Weight is the force due to gravity acting on a substance. I put that there because lots of times people tell me mass and weight are the same. They're not. The more mass something has, the more it weighs, but that weight is caused by gravity. Volume, like I said, amount of space it takes up. Now, matter includes things like solids, liquids, and gases. It does not include things like light, energy, and heat. These are forms of energy. Light is a form of energy. Heat is a form of energy. Sound is a form of energy. Those do not take up space. They do not have mass. They are not matter. Atoms, it says here the smallest unit of matter, but we're going to see that that's not really true. Atom is the smallest unit of an element. Okay? And so that begs the question, well, what's an element? An element is the simplest form of material because it contains only one type of atom. So there's different atoms for different elements. There's about 90 naturally occurring elements and around 20 man-made elements. We make those with particle accelerators and nuclear reactions. Now, we do know a little bit about atoms. We know they have protons, neutrons, and electrons. And of course, protons, which are these red guys in the nucleus here, they are called protons because they are positive. They're in the nucleus and they determine the identity and help determine the mass of an atom. And when I say identity, I mean hydrogen. All hydrogen atoms have one proton. All helium atoms have two protons. Okay? And if it doesn't have two protons, it's not helium. The next thing in the nucleus is, I guess we should say that. The number of protons is the atomic number, and if it changes, the element changes. The next thing in the nucleus is the neutron. That's represented by these green things. They have no charge. They're neutral. They help determine the mass of the atom. They have about the same mass as the proton. It is a little bit different, but close enough. We're going to say they both have a mass of about 1 atomic mass units. They're neutral. They determine mass. They also help keep the nucleus stable so we don't have a whole bunch of radioactive elements. Adding more neutrons does increase the mass, and it can also affect the stability. Of course, around the atom we have these electrons. They're found in a cloud around the nucleus. They're negative, and they determine chemical properties, like what bonds these things make, how well they react, and we'll learn more about that in our next couple sections. They are, like I said, involved in bonding and reactions. And of course, since atoms are neutral, we have to have the same number of negatives as positives. So the number of protons is the number of electrons for a neutral atom. Now, we have different numbers, atomic number and mass number. Atomic number is the number of protons in an atom, and it's a whole number on the periodic table. So you know the periodic table has little cells, and within those cells are all the different elements, and usually you have the symbol. This is the symbol for hydrogen. It's got a number, and then it's got another number. And sometimes it tells you the name, sometimes there's more information. This whole number here that increases by 1 every time as you move from left to right, that is the atomic number, and it is the number of protons. And remember, the protons tell us what the element is. And the periodic table then is arranged by increasing atomic number. As you move from left to right, it goes up by 1. Every time you start over on a row, you're increasing the atomic number. Mass number is the number of protons plus neutrons in an atom, and we learned about this when we were dealing with isotopes. And so this is always a whole number, so it is not this number. You can't have half a proton or half a neutron. This, as it turns out, is called atomic mass, and it's an average of all the different isotopes, and we're going to look at that in more detail a little bit later. Neither one of these numbers includes electrons. Electrons are very, 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 very small. They add almost no mass to the atom. If we know the number of protons, we know the number of electrons, so we don't need to count them. Then isotopes, remember, atoms of the same element with different numbers of neutrons, so they have the same number of protons but different numbers of neutrons, and we identify them by telling their mass numbers. So we can have carbon-12 or we could have carbon-14. Those are both carbon, and since they're carbon, they both have 6 protons, but they have different numbers of neutrons. So another way we write that is we could say carbon-612. That tells me it's 6 protons and 12 total particles in the nucleus. We also see carbon-14, and the 6 is still here. It's still carbon, so it still has 6 protons. 14 things in the nucleus must mean 8 neutrons. So we can write that in a couple different ways. Okay, that means not all atoms of the same element are identical because we can change the number of neutrons in the nucleus. So like I said, we write that name mass number. Okay. Then you guys looked at states of matter. We did a lab where we were freezing and boiling and melting water. And of course, all we're doing when we're changing states of matter is we're changing the arrangement of the particles. So in a solid, we have particles that are basically lined up and they vibrate in place, but they don't shift in position. In liquids, they are close together. There's pretty strong attractions between the particles, but they are allowed to flow past each other. And in a gas, these things don't really have very much of an attraction. They're bouncing all over each other. These last two states are called fluids because they can freely flow. Okay? So, like I said, particles are close together in a solid. They don't have very much energy because the particles are moving the slowest, and there's very high attractions holding those particles in place. Liquids, particles are a little bit further apart, medium energy and attractions. Okay, these two on the left, they have a definite volume. These two on the right, they have an indefinite shape. Okay, so solids have a definite volume, definite shape. Liquids have a definite volume but no definite shape, and a gas has neither. It doesn't have a definite shape or a definite volume. It can expand to fill its container, but it does have the lowest attractions and fastest moving particles. Okay. Then you guys went through a phase change, and remember, to do that we had to either add energy to it or take energy out, and we made graphs, and during the phase change we saw that the temperature did not change because it wasn't changing the kinetic energy of those particles, it was changing their potential energy. Now in an endothermic phase change, endo means into, so it absorbs energy, goes into the substance, and it goes from a low energy state to a higher energy state. So we have anything like melting or sublimation or boiling are all endothermic changes. Exothermic means it's going to release energy, go from a high energy to a low energy state. And so if we freeze something from a liquid to a solid, or vapor condenses or vapor deposits, we have exothermic changes. It goes from a high energy to a low energy state. This is an endothermic curve as we go up it, and it's exothermic as we go down it. So if we're adding energy to it, then it's endothermic because energy is coming in. If it's releasing energy to its surrounding as it cools and freezes, then it is an exothermic change. And finally, we did a little bit with chemical reactions. A chemical reaction happens when bonds break and new things form. So we break old bonds, we get new bonds. And that involves electrons, and we're going to be looking at that in more detail. But you can see, like, here's hydrogen gas, that's two atoms of hydrogen bonded together. Here's oxygen gas, two atoms of oxygen bonded together, and more hydrogen gas. We go through a reaction, and out pops water, two hydrogens bonded to an oxygen. They've changed. When that happens, energy is also involved. Okay? So electrons are involved in bonding. They're also involved in reactions, but we're not going to worry too much about this, at least not yet. Acid-base reactions can move hydrogen ions around, and a hydrogen ion is essentially a proton. Okay? We looked at the energy in an endothermic and exothermic reaction, and just like a reaction changes bonds and it changes the substance we have, it changes the energy we have. So in exothermic reactions, energy is released as heat, and so it's going to feel hot. Okay? The chemical potential energy, which is initially stored in the substance, was released as thermal energy. So we put a little energy in to get it started, whether that was stirring or mixing or dumping them together, and because of that reaction happens, they release a whole bunch of energy. So you'll see over here, the chemical potential energy started here and it ended down here. That means there's less chemical potential energy because it converted into thermal energy, which is energy related to the particle motion, and that causes an increase in temperature. Of course, an endothermic reaction happens the other way, but in either type, we need to actually make the reaction start, and that's what this activation energy is. So this bump here, we put in a little bit of energy to get the reaction started. You can think of that as like striking the match to light the fire. We have to put in a little bit of energy, we'll get out some energy. And then, of course, like I said, endothermic reactions, they absorb thermal energy from the surroundings, which means they feel cool because they don't just absorb that energy, it's then converted to chemical potential energy. So that means there used to be more thermal energy and now there's more chemical potential energy, so the amount of thermal energy goes down, it feels cool.